Okay, so next we will talk about example number 6, and in the previous video basically we talked about the concept of LCM. We now understand what LCM is. So the question is, let star be the binary operation on n given by a star b is equal to LCM of a and b, right? So you want to find, for example, part 1 of this question, you want to find the LCM of, or you want to calculate 5 star 7, which is the same thing as LCM of a and b, which is 5 and 7. So LCM of 5 and 7, based on what we said before, so basically 5 is the same thing as basically 1 times 5, and 7 is the same thing as 1 times 7. So the LCM of basically 5 and 7 is the same thing as, is a number that has a 5 in it. So a 5 is basically a 1 and a 5, and it also has a 7 in it. So basically a 7 is a 1 and a 7. So of course the ones are not required. You're not required to write the ones in here, because 1 multiplied by anything is going to be equal to 1, so you don't have to write them. So it's just simply going to be equal to 5 times 7, which is basically the two numbers simply multiplied together, right? 35. So as you can see, 5 is of course you can appreciate the fact that 5 is a prime number. 5 is a prime number. Also 7 is also a prime number, right? So then we can conclude from this basically exercise, you can conclude that the LCM of two prime numbers is just simply the product of those two numbers, meaning that you don't have to actually calculate the LCM of the two numbers. If you multiply them together, you will get the LCM of the two numbers. So that is that is one thing. So that's the same thing as 5 times 7, which is equal to 35, right? So that is the first part of this question. So remember that the LCM of two prime numbers is basically just simply the product of the two numbers. Second, we want to calculate 20 star 16. We want to calculate 20 star 16. Now 20 star 16 is the same thing as the LCM of 20 and 16. 20 and 16. Now 20 is the same thing as, if you prime factorize it, you get 2 times 10 and 2 times 5, which means that 20 is the same thing as 2 times 2 times 5. A 16 is the same thing as 2 times 8, 2 times 4, and 2 times 2, which means that the 16 is 2 times 2 times 2 times 2. So then what that means is that a 16 is the same thing as 2 times 2 times 2 times 2, and a 20 is the same thing as 2 times 2 times 5, right? Now, in order to calculate the LCM of 20 and 16, you're looking for a number that has a 16 in it and also 20 in it. So a 16 is the same thing as 2 times 2 times 2 times 2. A 20 is 2 factors of 2. I already have 4 of them, and a factor of 5. So that's a 5 over here. So that's the same thing as 16 times 5, which is equal to 80, right? 16 times 5 is equal to 50, and 30 is equal to 80, right? So that means that then basically the LCM of 20 and 16 is equal to 80. That's the second part. The the basically part 1 of this question. Now part 2 of this question is asking, is star commutative? Of course, of course, a star is, since a star A star B is the LCM of A and B, you can, of course, you basically based on the process that we use in order to calculate the LCM of two numbers, it doesn't really matter whether you want to calculate the LCM of 20 and 16 or 16 and 20, meaning that the LCM of 20 and 16 and the LCM of 16 and 20 is basically calculated in the exact same way, and they are actually going to be equal. And any two numbers that you pick from the set of natural numbers, or from the set of from any set for that matter, that's going to be the rule is going to apply, which is basically the LCM of any two numbers taken in any order is going to be the same. So yes, of course. So then you can say that since basically A star B is equal to B star A for every A and B belonging to N, therefore basically star is commutative. Star is commutative, right? Now, the third part of this question is you want to know if a star is associative, okay? And for this, we need to do a little bit of we need to basically do a little bit of an experiment. So suppose that you have, for example, three numbers. You have, for example, 20, you have 16, and you have, for example, 18. And suppose that I find the LCM of 20 and 16 first, and whatever that is. So let me start with the LCM of 20 and 16 first. Let's see what that happens to be. So a 20 is the same thing as 2 times 2 times 5. That's 4 times 5 is equal to 20. 16 is the same thing as 2 times 2 times 2 times 2. And 18 is the same thing as 2 times 3 times 3, right? Now, when you want to find the LCM of 20 and 16, basically what happens is that this number needs to have a 20 in it, meaning it needs a 2 and a 2 and a 5 in it. So a 2 and a 2 and a 5. And then you need a 16 in it, which is 4 factors of 2. So I already have 2 of them. So I add 2 factors of 2 here, and that is the LCM of 20 and 16. Now, this number, if I take the LCM of, basically, if I take the LCM, whatever this number is, now I want to take the LCM of this number 20 and 16. I want to take the LCM of this number with 18, meaning that I want to take the LCM of this number, basically 2 times 5 times 2 times 2, this number, and 18. I want to find the LCM of these two numbers. So of course this number needs to have basically this number in it, whatever that is. So I write it as 2 times 2 times 2 times 2 times a 5, and an 18 in it. And 18 is one factor of 2, which I already have here. and 2 factors of 3. So I add them here, or I multiply them here. So you can see that the LCM of this number, whatever that is, and 18 becomes this number, which you can write as 2 raised to the power 4 times 3 raised to the power 2 times 5. That is the LCM of basically these 3 numbers in this order that we did it. First we did 20 and 16, and then we took the LCM of that number with 18, right? Now what I want to do is that I want to change the order, meaning that I have the same numbers 20, 16, and 18, and now first I want to calculate the LCM of these two, and then take the LCM, find the LCM of that number with 20, right? So I calculate the LCM of 16 and 18. So 16 is the same thing as basically 4 factors of 2, 2 times 2 times 2 times 2, and 18 is a 2, which I already have here, 2 factors of 3. So that is the LCM of 16 and 18. Now I will calculate the LCM of this number, whatever that is, 2 times 2 times 2 times 2 times 3 times 3, and basically 20. So this number needs to have this number in it, which is 2 times 2 times 2 times 2 times 3 times 3, and 20, which is 2 factors of 2. I already have them here, and a factor of 5. So now this number is the same thing as 2 raised to the power 4 times 3 raised to the power 2 times 5. So as you can see, these two numbers, this number happens to be exactly the same as this number. Exactly the same as this number. 2 raised to the power 4, 3 raised to the power 2 times 5. And of course by the process that we are going through, you can of course conclude that any 3 numbers in any order that you take their LCM, the answer is going to be, the result is always going to be the same. And therefore you can say that because, and the reason simply is that because you are simply dealing with factors, and factors, it doesn't really matter, for example, whether you write it doesn't really matter whether you write, for example, 2 times 3 times 5, or you write 5 times 3 times 2, or you write, for example, 3 times 5 times 2, or you write, for example, I don't know, 2 times, 5 times 3, for example. All of these values are, all of these numbers are exactly the same number. So what that means is that the part 3 of this question, which is asking is star associative, you can say that basically since A, so you can say that since A star B star C is the same thing as A star B star C, for every A, B, and C belonging to N, therefore basically star is associative. Star is associative. Now, the next thing that we want to find here is basically we want to find the identity of star in N. Now, the identity of a star in N is basically based on the definition of identity. We said that, what is this thing? Okay, so we said that we had the definition basically in the previous videos, which was definition number 13, and that was basically given a binary operation star, given a binary operation star on a set A, which is A, the Cartesian product of A to A, an element E belonging to A, an element E belonging to A, if it exists, is called identity for operation star, is called the identity for the operation star if A star E is equal to A is equal to E star A. Of course, for every A belonging to A. This was the definition that we had. So based on this definition, basically any element that belongs to, based on this definition, coming back to this, to the problem that we had here, any element that belongs to N that you can find, if the LCM of that number with every member of the set N is basically the number itself, then you can say that let me write this down. So you can say that based on the definition 13, applying the definition to our problem, we have basically if there is some E belonging to N, such that if there is some E belonging to N such that E star A is equal to A star E for every A belonging to A, for every A belonging to N, of course, for every A belonging to N, then E is called the identity for the operation star. So in simple words, what that means is that you are basically looking for you're basically looking for a number that basically the LCM of that number and every other number in the set A, in the set of natural numbers, the LCM of that number with any number that you pick from the set of natural numbers is going to be that number that you pick in the set of natural numbers, meaning that, for example, suppose that you pick, for example, 2, which belongs to the set of natural numbers. Now I need another number E, right? And basically if I take the LCM of 2 and E, that should give me basically 2. If I pick another number, for example 3, which belongs to N, and if I have my E as well, then the LCM of 3 and E still has to be equal to 3, the same number that I pick here. If I have, for example, if I pick 4, which belongs to the set of natural numbers, and I have my e, then the LCM of 4 and e has to be equal to 4, and so on and so forth, right? So I think this number, I mean the identity for this operation in n is just simply 1, because 1 does exist to n, 1 does belong to n, and 1 does belong to n, and the LCM of 1 and a, you can say, is equal to a for every a belonging to the set of natural numbers. Meaning that, for example, if you pick, for example, I don't know, if you pick, for example, 5, the LCM of 1 and 5 is going to be equal to 5. If you pick, for example, 7, the LCM of 1 and 7 is going to be equal to 7. The LCM of, for example, 1 and 25,657 is going to be equal to 25,657, and so on and so forth. So that, I think that the identity is going to be equal to 1. And let me take a look at the solution here so that I'm sure about my answer. So yeah, thus the identity is 1. And therefore you can say that therefore the identity is 1. Now, of course, I'm going to rewrite some of these sentences in a more logical manner from the solution once we are done with the whole exercise, so that we are familiarized with a more formal way of writing these things as well. But basically, this is just to understand the example, and then we will write down some solutions as well. So you don't need to worry about if this part is a little bit messed up. Although I do my best always to write in the best way possible, but it's never going to be as logical and basically clean as the solution itself. So okay, so the next question that we have here to answer is basically which elements of n are invertible for the operation star. Which elements of n are invertible for the operation star. So we had a definition which was basically definition number 14. It was definition number 14, and that was okay. So the definition number 14 that we had was basically given a binary operation star on A, given a binary operation star on A, or basically in other words you can say basically a binary operation star on A. So you can write it this way as well, of course, with the identity element E in A, with the identity element E in A, and element A belonging to A is said to be invertible, and element A belonging to A is said to be invertible with respect to the operation star, with respect to the operation star, if there exists an element B in A, if there exists an element B in A, such that A star B is equal to E is equal to B star A. Then B is called the inverse of A. B is called the inverse of A and is denoted by A inverse. Okay, so based on this definition here what we are saying is that given a binary operation star on A with the identity element E in A, meaning that the identity element exists in A, an element A belonging to A is said to be invertible with respect to the operation star if there exists an element B in A such that A star B is equal to B star A is equal to E, which is the identity element, and then B is called the inverse of A and is denoted by A inverse. Now, applying definition number 14 to our problem, we have basically what the question that we asked was which elements of N are invertible for the operation star, meaning that if an element is so we said that basically some element A is said to be invertible with respect to the operation star if there exists another element B in A in such a way that A star B is equal to B star A is equal to E. So that what that means is that we are looking for all the numbers in N. Now I'm generalizing to our situation here. We are looking for all the numbers in N or let me write it this way, because that way I cannot actually talk properly about it. We are looking for every A belonging to N, for example. We are looking for every A belonging to N such that and basically in the previous basically case we showed that the identity is 1 here, right? Such that there exists another, such that there exists for every A, such that, let me write it this way, such that for every A there exists a B belonging to A such that A star B is equal to B star A is equal to E, which is equal to 1, right? because RE is equal to 1. So what that means is that now what this is implying, that we are looking at, this implies that we are looking for all A and B's where basically where the LCM of all those pairs of A and B's is equal to 1. Now, if you're looking for two numbers in the set of natural numbers where the LCM of those two numbers is 1, the only two numbers that you can find is basically 1 and 1, because any other two numbers that you take, for example, you take 2 and 3, the LCM of 2 and 3 is going to be equal to 6. Take the LCM of, for example, 20 and 16. That's going to be some number not equal to 1. And take any number that you take, the LCM is not going to be equal to 1 unless you take 1 and 1. So then you can say that, moreover, it is known that the LCM of A comma B is not equal to 1 for all A and B belonging to N. And of course, A and B not equal to 1. Which means that the only invertible number in N with respect to star is 1. And I suppose that is the right answer, as I can see in the solutions here. Now, this was, I suppose, the way that we wrote down this problem. I mean, the solution here is, in my humble opinion, it's logical enough. We don't really need to go back to the solution anymore. Although it doesn't really hurt to do so. So let me go over the solution one time and see if there is something that I can add here. So, for example, for the first part of this problem, we have, okay, so the first part is basically only calculating the LCM of these numbers, which we already did. Part 2 was basically the same thing. So, for example, for part 2, here we said that since A star B is equal to B star A for every, therefore that's also okay. So we don't need to rewrite part 2. Part 3, part 3 is also okay, we don't need to rewrite it. Part 4 is known that the LCM, let me take a look at this thing over here. Well, we don't really need to write anything else here. We are done with this exercise. So let's move to exercise number 7. So exercise number 7 is asking is star defined on the set 1, 2, 3, 4, 5. Number 7 is star defined on the set 1, 2, 3, 4, and 5 by A star B. By A star B is equal to LCM of A and B, a binary operation of A and B, a binary operation. So we want to know basically if a star defined on the set 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 by A star B is equal to the LCM of A and B. We want to know if that is a binary operation. So if I say that star is a binary operation on the set, for example, if I call the set A, for example, on the set A, then basically what that means is that the LCM of any of these two numbers that you take, for example, let's suppose that you take the LCM of 5 and 3. The LCM of 5 and 3 is going to be equal to 15. And you can see that 15 doesn't belong to A here, and therefore the image of, for example, the image of this A comma B does not exist in A, and so you cannot, and so this would not be a function, and therefore star is not a binary operation on this set, basically based on star. So then you can say that question number 7, the operation star on set A is defined as this thing. So to answer the question, basically they have answered the question in a much more basically. So what they have said is that the operation star is the solution. The operation star on the set A, which is equal to 1, 2, 3, 4, 5, is defined as A star B. A star B is equal to LCM of A and B. Then the operation table for the given operation star then the operation table for the given operation star can be given as follows. So you have 1, 2, 3, 4, 5. So you have basically all of these. Basically, let's say that this is 1, 2, 3, 4, and 5. 3, 4, and 5. And then you have 1, 2, 3, 4, and 5. And you can close this one as well, and this is star. And you have 1, 2, 3, 4, and 5. And you can erase the rest of this table. And then the table becomes basically, for example, 1 star 1 is basically the LCM of 1 and 1, which is equal to 1. 1 star 2 is 2. 1 star 3 is equal to 3. 1 star 4 is equal to 4. 1 star 5 is equal to 5. Meaning 2 star 1, for example, would be the LCM of 2 and 1, which is equal to 2. 2 star 2 would be the LCM of 2 and 2, which is equal to, of course, 2, right? And 2 star 3 is equal to 6 because it's the LCM of 2 and 3. 2 star 4 is equal to 4. 2 star 5 is equal to 10. So 2, 2, 6, 4, 10. And then you have 3 star 1 is equal to 3, 3 star 2 is equal to 6, 3 star 3 is equal to 3, 3 star 4 is equal to 12, 3 star 5 is equal to 15. 4 star 1 is equal to 4, 4 star 2 is equal to 4, 4 star 3 is equal to 12, 4 star 4 is equal to 4, 4 star 5 is equal to 20. 5 star 1 is equal to 5, 5 star 2 is equal to 10, 5 star 3 is equal to 15. 5 star 4 is equal to 20, and 5 star 5 is equal to 5. So you have 3, 6, 3, 12, 15, 4, 4, 12, 4, 20, and 5, 10, 15, 20, and 5. This is the operation table for the given operation star, right? Now, as you can see here, you can say that it can be observed that that, for example, 3 star 2 is equal to 6, right? 3 star 2 is equal to 2 star 3 is equal to 2 star 3, which is equal to 6, which of course does not belong to A, because A goes from 1 to 5, which does not belong to A. Or you can say that 5 star 2 is the same thing as 2 star 5, and of course you know that it's a commutative. I mean, the operation is of course commutative, but it's not a binary operation on this set. The set is actually is basically short of a couple of elements, basically, for star to be a binary operation on that particular set. So 5 star 2 is the same thing as 2 star 5, which is equal to 5 star 2, for example, is equal to 10, and 10 does not belong to A. Or you can say that 3 star 4 is equal to 4 star 3, which is equal to 3 star 4 is equal to 12, which does not belong to A. Of course, one of these examples is more than enough to show that basically that this is not a function, and therefore star is not a binary operation, right? But you can write, for example, 3 star 5 is equal to 5 star 3, which is equal to, for example, 3 star 5 is equal to 15, which does not belong to A. Or 4 star 5 is equal to 5 star 4, which is equal to 20, which does not belong to A. Hence, the given operation is not a binary operation. Hence, the given operation is not a binary operation, right? For star to be a binary operation, this has to be a function, meaning that basically under star, the elements of your domain has to be mapped to some image in the codomain of the function. Now here the problem is that the codomain of the function doesn't simply contain these elements, and so basically these cannot, for example, 3 star 2 cannot be mapped to 6 in the codomain of the function, and the reason is that 6 does not exist in the codomain of the function, and so it's just not a function anymore. And since it's not a function, star is not a binary operation. To tell you more clearly, I'm going to give you the notation, the definition. So definition number 10, as we said before, is a binary operation star. A binary operation star on a set A is a function star, and your domain becomes the Cartesian product of the set that you're talking about, and then your codomain becomes the same set. And we denote star of A comma B as, or by, basically A star B. So that means that this has to be a function, meaning that under star, every basically in this set, whatever you find is basically all of those ordered pairs of A comma B in such a way that A and B both belong to A and B belonging to A, of course, right? So all of these ordered pairs must be mapped to under star must be mapped to some element in A, basically in the set itself. But then the set A becomes the codomain of the function. Now in this particular case, the problem is that A does not have, for example, this element or this element or this element or this element, and therefore, well, this is not a function anymore, and therefore star is not a binary operation, right? Okay, so that was question number 7. The next question that we have is question number 8. Question number 8, which is basically, let star be the binary operation on N. Let a star be the binary operation on N, defined by A star B is equal to HCF, or highest common factor, of A and B. Is star commutative. Is star commutative? Is star associative? Is star associative? And does there exist identity for this binary operation on n? Does there exist identity for this binary operation on n? That is question number 8. Let's see how we can solve this problem. Okay, so now about this question. Basically the question is, let star be the binary operation on n defined by a star b is equal to the HCF of a and b. And we want to know if basically star is commutative, if star is associative, and does there exist identity for this binary operation on n. So in order to know whether star is commutative, of course when you take the HCF of two numbers, first we need to think about what is the HCF of two numbers. So that is the highest common factor of two numbers. So the highest common factor of two numbers is basically, so suppose that, for example, you're taking the highest common factor of 2 and 6, for example. HCF of 2 and 6. So 2 is the same thing as, for example, 1 times 2. 6 is the same thing as 2 times 3. So that the common factor between the two is between the two numbers is 2, and that's the highest common factor between the two numbers because it's the only common factor that exists between the two numbers, meaning that if you had, for example, some two numbers like, for example, let's say 4 and 12, 4 is the same thing as 2 times 2, and 12 is the same thing as 2 times 2 times 3. Now here you can see that 2's are common, these two 2's are common, so then you can say that the HCF of 4 and 12 is equal to, well, normally you take one, basically you have this, basically these two 2's that are common between the two numbers, so you take one factor of 2 for this pair and one factor of 2 for this pair and multiply them together, you get a 4. So 4 is the highest common factor of 4 and 12. But then over here, basically the only common factor that these two numbers can have or do have is basically 2, so the highest common factor of 2 and 6 is equal to 2, right? So that's basically, that is basically what the highest common factor is. And so by the process using which we find the highest common factor of two numbers, as you can see, it doesn't really matter whether you write the highest common factor of, for example, 2 and 6, or the highest common factor of 6 and 2. It's basically going to be the same thing. It's just going to be a 2. So these are going to be the same thing, meaning that A star B is equal to B star A. In this particular case, if A star B is defined as the highest common factor of A and B. And so, therefore, you can say that basically star is commutative, of course. So you can say that star is commutative. So let's call it part 1 of this question, part 2, and part 3 of this question. So part 1, is star commutative, you can say that basically since you can say that it is known that, now what I'm going to do is that I'm just going to combine my own thoughts and my own senses with the logical senses that I get from the solution, so that I don't have to basically go back over the solution one more time at the end of my own solution, right? That I think is much better. So it is known that the HCF of A and B, well, let me write it this way because I don't really know if that's basically standard notation. HCF of A and B is equal to HCF of B and A for all A and B belonging to N. And therefore you can say that A star B is equal to B star A for all A and B belonging to N. For all A and B belonging to N, thus the operation star, star is commutative. Is commutative, right? Now the second part of this question is star associative. Now let's take an example here and take a look at the process that we use in order to take the HCF of three numbers. So for example, let's say that you have a 6, a 12, and an 18. I will make this number a little bit larger. For example, let's make this a 24 or 24, for example. Okay. So now a 24 is basically the same thing as 2 times 12. It's 2 times 12, and that is 3 times 4, and that's basically 2 times 2, so that's 2 times 2 times 2 times 3. 12 is the same thing as 2 times 2 times 3. 4 times is equal to 12. And an 18 is the same thing as 6 times 3 is equal to 18. So that's basically 3 times 2. So that's 2 times 3 times 3. That's 9 times 2 is equal to 18, right? Now, I'll suppose that I take the LCM of these two numbers first. I'm sorry, the HCF. If I calculated the HCF of 24 and 12, that would be basically, so 24 and 12 would be basically 24 is the same thing as 2 times 2 times 2 times 3, and 12 is the same thing as 2 times 2 times 3. So you have a 2 common here, a 2 common here, and a 3 common here. So you have 2 times 2 times 3. Now if I take the HCF of this number, with 18, meaning that if I calculate the HCF of basically 2 times 2 times 3 and 18, so the number that I have is 2 times 2 times 3, and an 18 is 2 times 3 times 3. So I have a 2 common here, I have a 3 common here, So that's the same thing as 2 times 3. That's the same thing as 2 times 3. So so that's basically one part of this experiment. Now the second part that we will do is that we will find basically that we will find the HCF of, for example, 12 and 18 first. The HCF of 12 and 18 first. So 12 and 18 would be, what they have in common is a 2 and a 3. So that's 2 times 3. And then if I take the HCF of basically this number, 2 times 3, and basically, and 24, so what I have here is basically, so 2 and 3 and 24. So I have a 2 and a 3 over here. So a 2 would be common and a 3 would also be common between this number and 24, which means that the HCF of this number is 24, and 24 is simply 2 times 3, which is the same as this number. So since we are dealing with simply with factors, it doesn't really matter in what order you do them, meaning that from this you can conclude that, at least for this particular example, you can say that the HCF of 24 and 12, the HCF of if you take the HCF of 24 and 12 first, and then take the HCF of that number with 18, and then take the HCF of that number with 18, meaning that if I write it this way, right, that is going to be the same thing as taking the HCF of 12 and 18, taking the HCF of 12 and 18, and then taking the HCF of that number with 24. Right, and then taking the HCF of that. So that means that basically if A, B, and C, that means that if A, B, and C belong to the set of natural numbers, A star B star C is the same thing as A star B star C, meaning that the HCF, meaning that this means the HCF of A and B, HCF of A and B, and then whatever that is, you take the HCF of that and C. So that is the HCF of this and C, and that is equal to, this means the HCF of B and C, HCF of B and C, and then you take the HCF of A and this number. So that means that if A, B, C, all the three numbers belong to the set of natural numbers, then A star B star C is equal to A star B star C. And therefore you can say that star is associative. So now if I were to write all of this in a little bit more clearly or more logically, I would write this as basically for A, B, and C belonging to, for A, B, and C belonging to N, we have we have A star B star C is equal to the HCF of A and B, HCF of A and B star C star C, which is the same thing as the HCF of A, B, and C, right? Which is the same thing as HCF of A, B, and C, which we saw basically was actually the case, meaning that the HCF of A and B gives you some prime factors, and then once you do the star with C, then you are taking the HCF of C and the number that you get here, and practically you get the HCF of A, B, and C. And A star B star C, A star B star C is equal to A star, and that becomes the HCF of B and C, the HCF of B and C, and that is the same thing as the HCF of A, B, and C. Therefore A star B star C is the same thing as A star B star C. That's the operation, and of course you can write for all A, B, and C belonging to the set of natural numbers, and thus the operation star is associative. Now, about the third part of this question, we want to know, does there exist identity for this binary operation on n? Now, identity means that basically A star, what that means is that here we said that given a binary operation star on A, an element E belonging to A, if it exists, is called identity for operation star if A star E is equal to A is equal to E star A for all A belonging to A. Which means that we need to find some E in basically in N. So basically part 3 of this question, we need to find some E belonging to N such that A star E is equal to E star A is equal to E. Is equal to A. Which means that the HCF of any number that you take, and of course that is for every A belonging to N, right? Let me write this properly here. Such that basically A star E is equal to E star A is equal to E, if I'm not mistaken. Is equal to A. Is equal to A for all A belonging to N, right? So what that means is that we need to find some E, and when you take the HCF of, of course we established that star is commutative. So it's enough to show that, for example, A star E is equal to A, meaning that there is some E that belongs to N, and then the HCF of that E with any A that you can find in N is equal to A, meaning that the HCF of that number with any other number is basically that A itself, right? So what is, so for example, let's imagine that you have, for example, some number 2. Now you want to find another number, for example, E, such that the HCF of 2 and E is equal to 2. Meaning that the highest common factor of 2 and E is equal to 2. Meaning that they do not have any and I suppose the only number that you can find, is actually 1. Because if you take 1 is the same thing as 1 times 1, for example, and 2 is the same thing as 1 times 2. And, well, it doesn't work that way. I mean, it cannot be 1, because then the highest common factor would be 1, not 2. So, I think it doesn't exist. It cannot exist, because it cannot be, it has to be a dynamic number, meaning that, for example, for 2, if you're looking for some number in such a way that the HCF of this number 2, for example, and this A and this E becomes again the same 2, this again has to be 2. There is no other way. For example, if I pick a 3 over here, I'll get either 1 or some other number, but this number, I'll get this number only if basically E is equal to 2, right? So that means that E does not simply exist. So that's the operation. Now, an element E belonging to N will be the identity for the operation star if A star E is equal to A is equal to E star A for all A belonging to N. But this relation is not true for any A belonging to N. Thus, the operation star does not have any identity. As I suspected before, it doesn't exist. So you can say that basically for an element E belonging to N. Now an element E belonging to N will be the identity for the operation star, will be the identity for the operation star if A star E is equal to E star A is equal to A for all A belonging to N. But this relation is not true. But this relation is not true for any A belonging to N. For any A belonging to N, thus the operation star does not have any identity in N. That is basically question number 8. Now, the next question that we have is question number, I suppose question number 9, but let me see. They have 9, 10, 11, all the way up to 13. Okay, so we will continue this in the next video. Thank you.